Hi students, this is our lesson for section 6.9, Proofs Using Coordinate Geometry. Since I'm absent today, I made a little video for you that goes through exactly what we would have done if I was there in person. You should have your guided notes with you, and everything that's typed on my sheet is also typed on yours, but anything that's handwritten on mine, you should make sure you have copied onto yours. I apologize if you hear my dog in the background. She's outside right now. The warm-up that you completed is in front of you right now. It's talking about a rectangle with these vertices. So the picture should look something like this. I labeled them A, B, and C just so that I can refer to them in my work. Now, knowing that point A is 2A to the left and that point C is 2B up, and knowing that this is a rectangle, we can figure out what D is. We know that point D would be negative 2A, comma 2B. Now we are asked for the coordinates that of the midpoint of this diagonal here, connecting the fourth vertex, which is D, with the vertex across from it, which would be B. So in order to find the midpoint right here, we're going to need to use the midpoint formula. So we're finding the midpoint of segment BD, and you can see in my work I'm using the midpoint formula, and that will give me this, which will then simplify to 0B. So the answer for the warm-up is 0, B. The objective of today's lesson is to prove theorems using figures in the coordinate plane. I'm going to tell you right now that I'm not going to pause for long periods of time because this video has a time limit to it. So please, every time you're trying to copy a lot, please just pause the video so that you can copy what you need to and then play once you're ready. So today in section 6.9 we're talking about coordinate proofs. It is actually a proof, but it's not a two-column proof. Please remember everything I have handwritten you should be writing on your guided notes. Now, a coordinate proof involves mostly algebra, which means you're going to be using variables instead of numbers. And it's called a coordinate proof because it's in the coordinate plane. You're actually going to have some sort of figure that's in the coordinate plane. First, you're going to need to make a plan to determine what formulas you're going to use. These are going to be the formulas that we've been working with recently. You're also going to need to draw a picture. Every coordinate proof should have a picture to it, and the picture will be drawn in the coordinate plane because it's a coordinate proof. Sometimes the given and prove statements will be written, but sometimes they won't be. So you may need to write out given and prove statements. You'll see an example or two of that today. Now, the common formulas that will be used in coordinate proofs are the formulas we've been working with recently. So we know the slope formula is right here. If we have the same slope, we can show that two segments are parallel. If slopes are opposite reciprocals, we can show that they're perpendicular. We have the midpoint formula written right here, which is what we would use if we need to show that something is bisecting something else, or if we're working with the mid-segment in our coordinate proof. This is the distance formula, so anytime you need to find lengths, whether you're showing that something's congruent to something else or whatever it may be, you're going to use the distance formula for that. Now at the bottom here, we do have to keep in mind sometimes you will be squaring a binomial. It might not even show up in today's notes, but some of the problems in 6.9 will involve this. So I know we discussed this briefly recently, but please remember that's not just going to give you x squared plus a squared. Squaring something is multiplying it by itself, so you would need to write x plus a times x plus a, and then FOIL that and simplify. The first proof in your guided notes is referencing a right triangle, telling you that you have a midpoint of a side of it, and there's three things you basically have to prove congruent. Essentially, you have to show that they have the same lengths. Now, in order to do that, notice you're given the given and prove statements here, but you're not given a picture. You need to draw the picture, and the picture needs to be drawn in the coordinate plane. So spend a little time thinking about what the picture should look like. Where would it make sense for you to draw your right triangle? These are some possibilities, 6 different possibilities here for where you could draw a triangle in the coordinate plane. Now if you look at each of these, essentially you're trying to decide which of these options would involve the least number of variables so that your math can be as simple as possible. Like this one's a pretty good setup. You'll need a variable for however high this is, however far to the right this is, however far to the left this is. Keep in mind, I think these red triangles might look like isosceles right triangles. We're not told that. We're just told that it's right triangles. So we would not assume that that's the same length as that or anything like that. Now, if you look at this one, you're only going to need a variable for how far to the right this is and how far up this is, because you can use 0, 0 right here. So that simplifies it a lot. Same idea here, except you would need some negatives because we're down here. You're going to need variables for how far to the left this is, how far up this is, how far to the left this is, how far to the right this is. So that's kind of a lot of variables. In the last two situations, you would need a whole bunch of variables. So really the simplest version to work with here is going to be this. So you can see in my picture, I drew the right triangle where I said I was going to, and I labeled each of the coordinates of my triangle. Knowing that M is the midpoint of segment EF, I specifically, instead of labeling this as like A and this is B, I label them as 2A and 2B because I know I'm going to have to use the midpoint formula, so I'll wind up dividing by 2, which means that to avoid having fractions in my work, it would be easier to start with like 2A and 2B. So I'm going to use the midpoint formula to find M. When I do that, I get that M is AB. I kind of planned it to be that. So M is AB. And let's remember what we're proving here. We're proving that EM equals FM equals OM. So this has the same length as this, has the same length as this. So if we're talking about lengths, we need to use the distance formula. Now, in a coordinate proof, I didn't mention this very much on the coordinate proof slide here, but please make sure, obviously you have your picture, you have your given and prove statements, but as you're using formulas, before you use a formula, write what you're using, like what formula you're using and what you're using it to find. That is part of what I will be grading when I'm grading a coordinate proof. So this says you're going to use the midpoint formula to find M, because that's the first thing that we're doing. Again, that's part of what I'm grading. There isn't going to be a mini quiz on 6-9 next class. You will not have a mini quiz on this, but you will have a coordinate proof on your Chapter 6 test. So I used the midpoint formula. I got AB. I've labeled it here. And again, I said I'm going to use the distance formula next, so I'm going to write. Now use the distance formula to find EM, FM, and OM. So I'm writing what formula I'm going to use and what I'm going to use it for. Now I use the distance formula right here to find EM. And you'll see that I got the square root of A squared plus B squared. Now that cannot be simplified further. Sometimes students think that that could equal A plus B or AB, but it doesn't. Let's keep this little example in mind over here. If we have the square root of 9 plus 16, that simplifies to 5. 5 is not the same thing as if we had taken the square root of 9 and the square root of 16 and add them together. That would give you 7. And obviously it's not the same thing as 3 times 4 either, which would give you 12. The answer there is 5. So let's recognize that when we have something like the square root of A squared plus B squared, there is no way to simplify that further. Next, I used the distance formula to find FM. And I got the same thing. And I used the distance formula to find OM. And I got the same thing. So all three of these lengths are the same. So I'm going to finish my proof by stating, so by substitution, EM equals FM equals OM. So just like in a two-column proof, where your last step should be your proof statement, same thing here. What you were told to prove is the end of our proof. Because all of these measures are the same, we know that all three of these things equal each other by substitution. proof 2 does not give you a picture, does not give you a given or prove statement. You need to decide what you are given, what you are proving according to this statement, and you need to draw your picture. Again, think about what makes sense for a good picture for this proof. So here we're using coordinate geometry in order to prove that the diagonals of a rectangle are congruent. So obviously our picture is going to involve a rectangle in the coordinate plane. Now the most logical location for where to place your rectangle would be where I have it right here, in the first quadrant with two sides along the axes, so that we just have the least amount of variables possible. So I use that this side length of the rectangle is A and that this length is B, so that gives us A0 here and 0B here. And C, since it's a rectangle, it's going to be the same distance to the right, so that's also going to be A to the right. And it's the same distance up as B, so it's going to be B to the left. I'm sorry, B to the right. So I have AB for the coordinate of C. Now again, you're not given your given or proof statements here, and that is part of a coordinate proof. So you need to think, what's my given statement, what's my proof statement, and that will be part of what is graded. So notice this is saying prove that the diagonals of a rectangle are congruent. So we know that we have a rectangle, and what we need to prove is that the diagonals are congruent. So I'm given that ABCD is a rectangle, and I want to prove, well, if I come over to my picture, the diagonals are AC and BD, so I want to prove that AC is congruent to BD. Now, in order to do that, I am going to use the distance formula to find AC and BD. Remember, that is part of a coordinate proof, writing what you're doing, writing what formula you're using and what you're using it to find. We find that AC, when we use the distance formula, using this coordinate of 0, 0, and this coordinate of AB, that's going to simplify to the square root of A squared plus B squared, which we have recently discussed is not able to be simplified further. And same for when we find BD, it's going to simplify to the same thing. So to sum this up, remember this is what we wanted to prove. So I'll end my proof by stating, therefore, AC is congruent to BD because they have the same lengths. Now, I chose to place this rectangle like you see in this picture, and I explained my reasoning for doing that, but actually in past years, I set this proof up a little bit differently, and I want to show you that it would still work out even if your picture is in a different location, but it's going to be more complicated. So I know this isn't super clear, but this is another way to prove proof 2. There's nothing that you have to copy on this slide. So here you'll see I set my rectangle up so that it's centered about the origin. So I said, okay, if this is, this point C is A to the right and B up, then D is the same amount to the right and the same amount down, so that would be A negative B, and then this is negative AB, this is negative A negative B. So I did the same thing as far as use the distance formula to find AC and BD, and you'll see my algebra is just a little bit more complicated. Here I have A minus negative A, which is 2A, so I have to square 2A. So 2A, quantity squared, 2A times 2A is 4A squared. Same idea here. B minus negative B is going to give us 2B. When we square that, 2B times 2B is going to give us 4B squared. So I wind up with the square root of 4A squared plus 4B squared. Again, that cannot be simplified further. Really, the order of operations tells us we would have to do what's inside the grouping symbol, which the square root symbol is a grouping symbol, so we'd have to do what's inside before we actually took the square root of it. So no way we can simplify what we have there. And we finish it the same way, stating therefore AC is congruent to BD by substitution. Really, these should have bars on top for showing that they're segments.